Section 4.1, areas and distances. What we're going to do is we're going to try and find the areas under curves. We're going to start with this curve right here, where we've got 4 minus x squared. That's going to be a parabola, opens downward. We're going to go from 0 to 2. So we're going to say this is 0. Let's go over here is 1, over here is 2. And coming up the y-axis, let's call this 1, 2, 3, and 4. Now, for a graph, this is down opening parabola. At a value of 1, I think the value of this function is 3. So I got my down opening parabola and something like that. All right, now let's estimate the area under the curve. Well, let's be kind of lazy, and let's make one rectangle. Let's make one rectangle, and let's estimate the area under this curve. Now, the highest part of this curve is located over on the left-hand edge. So let's use the left endpoint of this region to find the area of this rectangle. So if I do that, I would say, okay, my height at the left edge, because that's the highest edge, it's right here. That's the height, and now I'm going to make one rectangle, so I get all the way over to x is 2, and there's my rectangle. Well, you can see we have included a whole lot more area than what is actually under the curve. That rectangle is 4 units high, it is 2 units wide. We'd say the area is 8. Well, that's a pretty gross overestimate. So now let's make an underestimate. Let's use the endpoint that has the lower value on the rectangle. But we will use the left endpoint. And if we use the left endpoint, the left endpoint is right over here. And so if I use that as the height is 0. The width of this supposed rectangle is 2 units wide, and we would say, well, the area of this region is somewhere between 0 and 8, and we haven't really narrowed it down very well, and it's really not a very good estimate. So how could we do a better job? Well, I guess what we could do is we could, since rectangles are really easy to find the area, let's just make one. Now again, we're still pretty lazy. So let's only make 2 rectangles. Let's make 2 rectangles. Let's again, because the left side of this has higher values, let's use a left endpoint estimate. And 2 rectangles, the first one's going to go from 0 to 1. And I'm going to go up on the left side of this until I hit, and then I'll go over and I'll say, okay, now this rectangle has a width of only 1. So this rectangle is 4 high. It is 1 wide, has negative 4. My next rectangle goes from 1 to 2, and I'm going to use the left endpoint because the left endpoint is higher. I'll go up until I hit. I'll go across. My rectangle, that is 3 units high by 1 unit wide, and we're going to get area of 3. So a total of 7. So our upper estimate is going to be 7, not 8. Now what about a lower estimate? Okay. Again, I'm going to notice that if I make rectangles using the right endpoints, right endpoint of the region, if I go from 0 to 1, what's higher? The left side of this or the right side of this? Well, the right side is lower, so if I want a lower estimate, an underestimate, I'm going to use that to determine the height and bring my rectangle back this way. Now, certainly I missed out on a bunch of area up here. So this is going to be a definite underestimate. This one is 3 units high. It is 1 unit wide, area of 3. And now if I'm going to go from 1 to 2, well, again, it's the right endpoint over here that has lower value. So I'm going to use that to determine the height. This is going to be 0 high by 1 wide, area of 0. So a total of 3 units. So my new estimate is that the area, not just between 0 and 8, but I'm going to say it's between 3 and 7. Not as good, but better than what we had before. More rectangles we make, better our estimate's going to be. Now we have a program on our calculators called Areas 1. And we're going to use this to estimate the area under the curve. So hopefully you have Areas 1 on your calculator. And what we're going to do is we're going to fire up that program. And we're going to fill in this table. Now, if I, using this exact same upside-down parabola, still going from 0 to 2, if I tell my calculator, because it's a little busy work, I want to make left endpoints, and I'm going to go from 0 to 2, I'm going to make 10 rectangles. Well, what the calculator is going to give me, it's going to give me my estimate using left endpoints, midpoints, and right endpoints. So if I'm talking about a midpoint, I'm talking about, well, let's see, let's do this. If I've got this same parabola, and I'm going to go from 0 to 1, I'm going to determine the height at the midpoint. Until you hit, say, okay, that determines my height. Now that's a pretty nice estimate because I got a little too much here, but I got a bit of an underestimate here, and they somewhat balance out. Not perfectly, but they somewhat balance out. So a midpoint is just where you're making a rectangle, but determining the height at a midpoint. Now, if I put these numbers into my calculator correctly, I do believe that it's telling me my area using a left endpoint's 5.72, midpoint 5.34. Now 10 rectangles narrows this area down. It's somewhere between 4.9-ish and 5.7-ish. Can I narrow it down more? Have my calculator make 50 rectangles. Well, now I see that my area is somewhere between 5.2-ish and 5.4-ish. And calculators are great things. They can do a lot of busy work in a short period of time. If I were to make 100 rectangles using left endpoints, there's my area. Right endpoints, there's my area. And right endpoints. So the area is somewhere between 5.29, 5.37. And as we saw, as we drew our midpoint rectangles, those are pretty accurate. I bet you our actual area is somewhere around 5.33. So as the number of subintervals and the number of rectangles increases, the accuracy of the area increases as well. We should make as many rectangles as possible. Our calculators, lots of them are possible. They give us a formula. Well, they give us an expression for how we're going to find the area. And here's the area making right endpoints and making left endpoints. But in general, what we're going to do is we are going to take f of x, which is the height of each rectangle. We're going to multiply that by delta x, which is the width of each rectangle. And you recognize that notation? summation notation, we're going to add all of these guys up. Two rectangles, 10, 50, 100. In fact, what we're going to do to be really, really accurate is we're going to add up an infinite number of rectangles. Now, that's going to be pretty tough for us right now. Calculator can't even do an infinite number with what we've been doing with this program. But our goal to get the most accurate possible estimate for the area under the curve is to make an infinite number of rectangles and add their areas together. Now, distance. The distance an object travels is the signed area trapped by the velocity function and time. If we've got a velocity time graph, the area under the curve gives us distance. I'm writing that down. Yeah, distance. Equals area under velocity time graph. And actually, for those of you who have taken physics, distance here really should be called displacement. How far I am from where I started. If your velocities are always positive, your distance and your displacement are going to be the same. But if you have a constant velocity, okay, this is velocity, this is time. What if you have a constant velocity? And we're going to have times that are greater than 0. Let's see. How far have we traveled between a time of 0 and a time t sub 1? All we'd have to do is find the area of this rectangle. This is already a very nice recognizable shape. Now, what if we had variable velocity? Now, it does say here, if velocity is greater than 0, the object is moving to the right or up, and that's no surprise. Negative velocities mean the object is moving to the left or moving down. So what if I start with a negative velocity? And the velocity eventually becomes 0, and the velocity eventually becomes positive. And this is velocity, and this is time. What is my displacement between the time of 0 and the time of 1? Well, let's find the area under the curve. Because it says, and again, this word right here will be displacement. The displacement is the signed area. So this has an area, but since it's located below the x-axis, we're going to consider that displacement to be negative. It was moving to the left. Its velocities were negative. And so it was moving to the left in the negative direction. It then stops and has a positive velocity after that. So that means it is now moving to the right, and it has a positive displacement. And the way I've drawn this one, it looks like these two balance out pretty darn well. And so my displacement appears to be equal to 0. Now distances, remember distances are always positive. So I would take the absolute value of this area plus, it's already positive, but I'll do it anyway, the absolute value of that area, and that would give me the distance. What is the distance that I travel? Distances are always positive. Now, use the information from this table to find the distance that the car has traveled. All right, I'm going to go from a time of 0 to a time of 30. And I'm going to do 6 intervals. using left endpoints. Now, since these are velocities and times, my rectangles, when I take my height times my width, feet per second times seconds is going to give me feet. I am going to get distances. So my first rectangle is going to be 5 units wide. And if I use the left endpoint, I'm using 0. Plus the next rectangle, again, 5 units wide, 5 seconds. And I'm going from 12 to 26, but if I'm using the left endpoint, I've got to use the 12. In fact, all of these are 5 units wide, aren't they? And my next left endpoint would be 26. And on and on and on. My next interval goes from 42 to a velocity of 60. I'd have to use the left one. And I trust you could do that on your own. If I were to use right endpoints, it looks like it's going to be the same thing. And I can be a little more efficient with the way that I show them to work. My first rectangle. So my first rectangle is going to go from 0 to 5. The right endpoint is 12. All of these rectangles are 5 units wide. My next one goes from 12 to 26. 26 is on the right side. 42 is on the right side. 60 is on the right side. 62 is on the right side. And 64 is on the right side. And that's just a more efficient way of finding our area under the curve. Now, if I use midpoints, I've got to use values that are actually in the table. And if I'm going to use values that are in the table, I can't use an interval that is 5 units long. Because if I go 5 units wide, what is the midpoint down here? Well, I don't really know. I don't know that at the midpoint, at a time of 2.5, I've got a height of 6. I can't say that for sure. I've got to use information that's in the table. So instead of using 6 intervals, I can only use 3. If I go from 0 to 10, I know that that is 10 units wide. In fact, all of these are going to be 10 units wide. But I do have information on what's going on at the midpoint. The height of that rectangle is going to be 12. The height of this rectangle that goes from 10 to 20 is going to occur right here. And the height is going to be 42. And my final rectangle that goes from 20 to 30 will have a height of 62 at the midpoint. So you can use your calculators and you can figure out what those come out to be. That's how we're going to find area under the curve using a specified number of rectangles and data that either comes from a function or from a table or from a graph.